Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar Lecture Theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Friends, welcome to the 25th lecture on the SwayamPrabha course titled Maritime Structures, Types, Construction, Pre-Service Analysis and Design, offered by Department of Maritime Engineering at IIT Gandhinagar. I believe that you have gone through the previous lectures because the lectures what we are now proposing in this course are sequential. So it is better that you don't skip the order of these lectures and therefore you try to follow the full content of the course in a very clean manner. Having understood the different structural forms, the different construction processes, then special loads like fire, explosion and blast, it is inevitable and very important for us to now know what are the environmental loads that act on maritime structures, how to compute them, what are the equations and numerical systems available to us to compute them, how accurately one can estimate them, can you forecast them, and what is the influence of these loads on the design of maritime structures. Welcome friends to the 25th lecture where I am going to talk about environmental loads. In this lecture we say environmental loads 1, we talk about wave loads. Sea waves are a very important component of environmental loads acting on marine structures. So, friends, environmental forces on maritime structures essentially have two components. They vary spatially, that is, the location of the magnitude of wave and the period of wave is different at different geographic locations. It may be different in US, it can be different in India, different in Thailand, Korea. So, spatial variation plus it also varies with time. So, from the principle of physics, we know that any load which varies its intensity in terms of its spatial and time as well as in position are generally identified as dynamic loads. Okay? So, by that instance we can say that sea waves or the loads generated by sea waves are dynamic in nature. Therefore, there are two ways to classify them. You can classify them by two ways. One, you can classify them based on the physical phenomena. Two, you can also classify them based on the uncertainty. Now, one may ask me a question, why wave loads computation are uncertain? You know, environmental loads like wave loads are arising from nature. We really do not know what will be the wave amplitude, what will be the period and direction of wave at any geographic location, because it is influenced by the gravitational effect between the earth and moon. Therefore, friends, there is a high degree of uncertainty associated with computing these waves in a very accurate manner. So, I can straightaway say it is very difficult to forecast these wave loads well in advance. However, there are stochastic models available in the literature, very advanced models which help you to forecast them, to estimate them close to the accuracy, but however, we will keep our fingers crossed as a maritime engineer, saying that they are only can be modeled with certain degree of uncertainty for design purposes. Then the question comes, how in design this uncertainty is handled? Because if you do not know the load, you cannot design the structure. Obviously, you are right. So, when you cannot have any certain value of amplitude or any load acting on the structure, the uncertainty needs to be handled by a factor, what we call as load factor. We multiply certain number. I do not say it is the arbitrary number, there are rational basis to arrive at this number, but we multiply some factor to the load and I call that as a factored load. You must have heard this term in design of structures, especially when we do limit state design. Okay. So, possibly you will remember even the number, we multiply a number of 1.5 for dead load and live load and 1.2 for earthquake load, which is more common in most of the international codes of practice, including Indian codes. However, these numbers are not arbitrary, there are basis on which these numbers have been arrived at. Okay. We enhance the value or amplitude or magnitude of these loads by 50%, 20%, etc. So, we multiply a factor. So, the uncertainty is handled in a different manner in the design. However, we do agree that these forces come with certain degree of uncertainty. But the other classification we look at based on the physical phenomena, you can classify them very conveniently, which we are going to now see. Okay. Before we start about understanding wave loads, let us ask a question. In maritime structures, what are the major type of loads? That can act? Which can have dynamic effects. So, then we can say the functional load arising from operation of machinery, mechanical equipments, HVAC, drilling equipments, etc. This is one classification. The second could be the environmental loads arising from nature. So, friends, we stay here. So, in maritime structures, when we talk about loads causing dynamic effects, we stand here and saying we form or we constitute a major classification of loads acting on maritime structures. Okay? If you have any dynamic load acting on a system, you want to account for its influence on the structure, you generally try to find out the dynamic amplification factor caused by this load. Okay, we generally do that. We will talk about this in detail when we touch upon the basics of dynamic analysis in the further lectures down the line, but like we have used something called load factor to account for uncertainty, we also have something called dynamic amplification factor to account for the dynamic effects of these loads. Okay. Furthermore, friends, to recollect a memory, we have said that maritime structures have their fundamental periods varying from 2 to 5 seconds if they are fixed type, varying from 120 to 150 seconds if they are floating type. Why we are asserting about or why we are bothered about the time period of this structure? It is very important, friends, from the basis of physics. If this period coincides with the natural period of the load, then you can expect something called resonating effect. So, it is very important for us to avoid the resonating effect on structures, because the resonating effect will always cause destructive influence on the structures. So, then what we have a control on this? We do not have a control on what is the period of the environmental loads, but we can always have a control on how to check that these periods do not fall in the band of natural periods of the structure. So, natural period of the structure, for example, if you really found out natural frequency of a system of a single degree, it is stiffness of the system by mass of the system. So, I can always play around with the stiffness and mass of the system, which essentially comes from the geometry of the system, so that the natural frequency of the system does not lie in the same band as that of the exciting force to avoid resonating effect. Okay? So, we will not get into this in detail at this moment now, we will talk about this much in detail in the coming lectures. Okay? Therefore, friends, we now have the load fluctuations with time. What do you mean by that? Load is varying with time. So, what are the characteristics of the load that varies with time? Let us take for example the wave load. Wave load has got two essential parameters which varies with time. One is the wave height, otherwise called as wave amplitude. The other one is the wave period, otherwise simply called as period. In addition to this, there are many other issues, parameters which also vary with load. One such thing is the direction. Okay? So, spatial variation. For a minute, we will neglect this, we will take these two. Then we say that this variation with time can be again subdivided into two parts. One we call as macro scale variation, the other one is the micro scale variation. Friends, the macro scale variation does not bother the structure much. Okay, it is good about it. So, we do not have to really bother about this. The micro scale variation affects the dynamic response significantly. Therefore, we should have a concern on this when we do a dynamic analysis of maritime structures. Let us quickly have some example of macro scale variation. They could be average wind velocity. I am saying average wind velocity over a period of time, because the moment you say average, you have to mention the period. Second, the tidal current. Third, significant wave height. And the wave period. The third one could be peak ground acceleration of earthquake motion. These are called as macro scale variations. There will be variations in this, but the variations are marginal. Okay? Then what are micro scale variations? Examples. In micro scale variation, the structure response is significantly influenced by these variations. Okay? So, they will give rise to dynamic effects on structures. Okay? So, one such case, what we will discuss today is the sea waves. Therefore, friends, the loads generated from sea waves are called as hydrodynamic loads. You may ask me a question, why the term hydro? Because it is from water. Why the term dynamic? Because it varies in space and time. We already saw that. Okay? So, hydrodynamic load arise from sea waves. Okay? Let us quickly understand how actually sea waves exhibit forces. Okay? Sea waves are actually wind generated surface waves. I can give a very simple example. Let us say I have a water body which is purely horizontal. Okay, water anyway adopts an horizontal level, we all know that. What I do, I put a ball on this top, float, a simple ball which floats on the top. Okay. Now, when the water level is purely horizontal, when there is no external force acting on the ball will not move, is it not? Ball will remain there. When the wind blows, over the sea surface, the horizontality of this sea surface is lost. It will start creating waves. Therefore, when the ball moves because of the wind action, the ball also follows the same path. It goes up and down, and of course, it moves laterally and longitudinally. Okay. So, now this fluctuation, what you see in the sea waves, is essentially because of the, I think ma'am, this is screen locked. This is essentially because of the wind waves. So, we now say sea waves are generated because of wind. Okay. So, wind generated sea waves. So, wind generated sea surface waves are producing, so wind generated surface waves on ocean produce large number of regular waves. What do you mean by regular waves? Regular wave is one which assumes a sinusoidal profile. It is called a regular wave. In reality, the sea surface elevation is random. Okay. What I say, this random can be a series of sum of many regular waves of different amplitude, of different period, of different phase lag. If I add all of them together, I may land up in this kind of signal. So, I pick up any one specific wave from this group, I call that as a regular wave. Okay. So, regular waves, series of them have different amplitudes and different direction. Okay. Now, I want to express them in a mathematical form. So, let us take a simple example of a sea wave, which is a regular sinusoidal wave. Now, this elevation of the sea wave is indicated as sea surface elevation, which is indicated as eta of t. It varies with time. Okay. When I put a ball on the top, since this wave is wind generated, the ball moves horizontally and the ball moves vertically. Okay. So, I now have horizontal and vertical velocity and acceleration of the ball. I do not call this as ball anymore, I call this as water particle. Okay. It is a water particle. This blue one is a water particle. This water particle moves vertically and horizontally. Is it not? So, I call this horizontal velocity as u dot and vertical velocity as u dot, v dot, and u double dot and v double dot are the accelerations. So, u stands for horizontal, v stands for vertical. Together, we call this as water particle kinematics. Okay. Water particle kinematics. Therefore, friends, now I will express sea waves to cause hydrodynamic effects using u dot, v dot, u double dot and v double dot. Okay. So, these are called water particle kinematics. Suppose if I try to understand the equations of these kinematics, what it will now give me? These kinematics will now give me forces, because you know, in a regular sea wave, when the ball or when the water particle starts moving horizontally and vertically, there is a force which is pushing this ball, right, or pulling this, whatever maybe you can assume. So, that force is a hydrodynamic force, and we all do agree from the fundamental principle of mechanics that if I have the hydrodynamic forces to be computed, this will be the function of velocity and acceleration. Okay, this is understood from the principle of kinematics. Okay. Now, how do we compute these wave forces? Now, wave forces are computed based on the water particle kinematics, which is given by different wave theories. There are different wave theories available in the literature which gives you this. So, these wave theories help me to calculate the water particle velocity, the water particle acceleration and the dynamic pressure exerted by this on any body. Okay. And all of them will be a function of, sea surface elevation. Friends, what is sea surface elevation? I have a regular wave which is a sample of 1,000,000 waves causing the sea waves. This profile of the sea wave is what we call as eta of t, which is called sea surface elevation. So, the water particle kinematics, dynamic pressure are all derived from wave theories, and wave theories explicitly tell that they are all function of sea surface elevation. So, my job is now to define the sea surface elevation and subsequently the water particle kinematics based on different wave theories, is it not? That is what we are looking at. Okay. We will take up a very simple theory first. So, the foremost and basic popular theory available in the literature is Airy's theory. Is Airy's linear wave theory. Okay. Let us just draw a single regular wave, sinusoidal. This part is called as the crest of the wave, this part is called as the trough of the wave. From the crest to the next crest, we call this as wavelength. It is also ascertained as wave period. It is also true can measure this from the trough to the trough also. Okay, it is going to be same because it is a regular wave. Now, this is my water depth seabed. So, if this is my water depth measured from the mean sea level, this is called mean sea level, okay, still water level. This is water depth indicated by D, okay. These are some basic nomenclature, and this is the propagative wave direction. Wave propagates like this from left to right on the screen, okay. Now, certain theories state something called long crested waves. If you have a long crested waves, then the water particle flow can be idealized as two-dimensional flow. Then the flow can be characterized using wave height, wave period and water depth. So, you need three parameters to characterize them. Let us draw a single wave and explain these three parameters. Water depth D, wave height is from the crest to the trough. This is wave height indicated as H. It is also called as wave amplitude. And from 0 to the next 0, full cycle, we call this as wave period indicated as T. So, if I know wave height, if I know wave period and water depth, I can characterize the wave to find out its kinematics. Any doubts, questions, friends? If you have any one of them, please note down, write to us in the discussion forum. We will try to help you understand that more in detail. Okay? Having understood a simple regular wave and we take a sinusoidal form of this wave as I am drawing on the screen now, a simple sinusoidal form. This is a typical regular wave which is used to explain the Airy's theory. Okay? The Airy's theory is commonly used to express the velocity and acceleration of water particle, which we call as kinematic quantities. It assumes linearity between the kinematic quantities like velocity, acceleration with respect to wave height. Therefore, Airy's theory is called Airy's linear wave theory. Okay? It assumes a sinusoidal form, a classical sinusoidal form as I have drawn on the screen, which is represented by wave height, wave period, and of course wavelength and water depth. Okay. So, we say wave height, wave period, wavelength and water depth. We will talk about this wavelength slightly later. So, now for this elevation of eta of t, since this is the wave propagation, I can now rewrite this as eta x of t, because it varies with space and time. So, let us say eta x of t. So, let us see what is the equation to find eta x of t. Eta x of t, the sea surface elevation, is given by h by 2 cos kx minus omega t. Okay, where k is called the wave number, equation 1, k is called the wave number, which is equal to 2 pi by lambda, where lambda is called the wavelength, which is approximately equal to 1.56 t square, where t is called the wave period, which is equal to 2 pi by omega, where omega is called the wave frequency in radians per second, wavelength is in meters, wave number is a simple number and period is in seconds. Okay. We can also have something called Cp, which is called the phase speed, which is actually omega by k. Okay, omega by k. Omega is known and k is known, I can always find out that. So, if we substitute back, omega is 2 pi by t and k is 2 pi by lambda. So, I think phase speed actually comes to be lambda by t, am I right? Lambda by t. So, friends, once I know the sea surface elevation, we already said the water particle kinematics depends on this for a linear wave theory. Let us write down those equations. So, now I say the horizontal velocity, water particle velocity, and the vertical water particle velocity are given by omega h by 2 cos hyperbolic ky by sin hyperbolic kd of cos kx minus omega t. Equation 2, the vertical water particle velocity. Now, I can also write this equation as a function of eta. I can also say, because eta is the sea surface elevation, eta x of t is h by 2 cos kx minus omega t, is already here, h by 2 and it is already here. So, now I can write u x of t as omega cos, let me write it here, u x of t can also be written as omega cos hyperbolic ky by sin hyperbolic kd of eta. I can call this equation number 2a. Now, what you do not know in this equation? Let us see, if I draw a simple regular wave, I know wave h, I know wave period, I know water depth, and hyperbolic is a trigonometric function, I think you know that, sin hyperbolic e power x minus e power x by 2 cos hyperbolic is e power x plus e power minus x by 2. We know this, where x the variable. So, here the variable is ky. K is a wave number, we already know that. So, what we do not know in this equation is y. Okay. So, let me draw the figure again. Draw a regular wave or the water depth, and y is measured from the mean sea level in this direction. So, how it is helpful for us? For example, if I have any point here whose y is known to me, okay, I can always find eta x of t, u x of t, v x of t at this point A. Okay. So, as you know, the wave force varies with space, varies with time, varies with depth also, is it not? So, I can find this. So, u x of t, u dot x of t is here. Let me write down the equation for v dot x of t. The vertical water particle velocity v dot x of t is given as omega h by 2 cos hyperbolic, sin hyperbolic ky by sin hyperbolic kd of sin kx minus omega t. Sorry, this is cos kx minus omega t. One moment, let us check this. I will write this equation again. The vertical water particle velocity is given as omega h by 2 sin hyperbolic ky by sin hyperbolic kd of sin kx minus omega t. Okay. Let us also borrow the previous equation in the same screen. So, horizontal velocity was given by cos hyperbolic ky by sin hyperbolic kd of cos kx minus omega t. This was equation 2. I am saying this is equation 3. So, if I know the velocities, can always differentiate this with respect to time and get the accelerations. Let me write down that. I can now write u double dot t as I differentiate this u double dot t, I get omega square h by 2 cos hyperbolic ky by sin hyperbolic kd of sin kx minus omega t. I can also write v double dot x of t, that is vertical water particle acceleration, as minus omega square h by 2 sin hyperbolic ky by sin hyperbolic kd times of cos kx minus omega. So, I will call this equation as equation number 4. Equation number 4, this is equation number 5. So, now friends, I have the water particle kinematics available with me as equation 2, 3, 4, 5, and equation 1 gives me the sea surface elevation. Am I right? Now, In the earlier lectures, we discussed about shallow water, deep water and intermediate water depth. Okay, let us now define this in a proper format. If I say the water depth exceeds lambda by 2, we call that as deep water. Okay. In shallow water, the water depth is lesser than lambda by 20. Of course, in intermediate water depth, the water depth is between lambda by 20 and lambda by 2. Okay. Earlier friends, we thought that the water depth as 150 meter, 200 meter, 1000 meters will only say is a deep, ultra deep, etc. Actually, they are discussed, they are classified based upon the wavelength, as you see on the screen here. Okay, lambda is the wavelength, we already know that, and d is the water depth. Now, to add to this, let us make a statement saying, if it is a deep water, then phase speed is independent of depth, of water depth. If it is a deep water. If it is a shallow water, phase speed depends on water depth only. But not on eta of t. Eta of t is the sea surface elevation, or not on the function of, not as function of wavelength. If it is intermediate, then phase speed will be uniform. One may wonder, what does this phase speed do in our design? It is very important component of design. Let us talk about this when we apply to this for calculating the wave forces. Okay friends. So, in this lecture, let us go to the summary. In this lecture, we discussed about the environmental loads, their classification, their micro macro scale variations. We talked about hydrodynamic effect, we talked about wave loads, we started using regular wave, we discussed about Airy's theory, and we found out equations for sea surface elevation, water particle kinematics, and so on. If I am able to continue this further and explain how to get the forces based on this, my job is done, is it not? So, let us see how one can find out the force based on this as well in the next lecture, and move on to the other environmental load, which is the wind load. Okay? So, if you have any doubts, please post it to the discussion forum in SwayamPrabha. Instructors will be able to attend to your questions and clarify your doubts to the best possible manner within the shortest possible time. Please encourage your friends to look into these videos and understand them in detail. Also do refer to textbooks as we advised in this course. Thank you very much. Namaste.